Hello everyone. So today let's solve the problem Bear and the Forgotten Tree 2, right? So this was asked in the India Hacks 2016 online edition, division 1 plus division 2, both for the division 1 and 2, right? So let's see what the question states. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here. So we have been given n vertices, right? So we have been given n vertices and m forbidden ordered unordered pairs and m forbidden unordered pairs and an integer k, nmk, right? So we have been given n vertices, m forbidden unordered pairs and an integer k. So what we need to do, we have to check whether there exists a tree on n vertices. There exists a tree on n vertices such that one, right, such that one or none of the forbidden pairs are edges, and this one, second point is vertex 1 has exactly degree k, right? So we have to check whether there exists a tree on vertices such that none of the forbidden pairs are edges, right? Such that none of the forbidden pairs are edges, right? So this one, let me write it, this one, this is the first point. And also this one, vertex 1 has exactly degree k, right? So vertex 1 has exactly degree k, right? So we have to print possible if at least one such tree exists. Let's meaning we have to print possible, we have to print possible if exists at least one such tree. We have to print possible if at least one such tree exists, otherwise we have to print impossible, right? Otherwise we have to print impossible, right? So or otherwise not or, let me write here otherwise. So this one we have to print impossible, right? So just remember this one. So what the question states here, I'll just read out this one loud, just try to remember this one. So we have been given n vertices, m forbidden unordered pairs and an integer k, right? So we have to check whether there exists a tree on n vertices. There exists a tree on n vertices such that none of the forbidden pairs are edges. None of the forbidden pairs, whatever the pairs have been forbidden, none of the forbidden pairs are edges, and vertex 1 has exactly degree k, and vertex 1 has exactly degree k, right? So these two things we have to remember, it's very important, right? So we have to print possible, if at least one such tree exists, right? Otherwise we have to print impossible, right? So this is the question, very simple, right? So let me delete this one entirely. Now let's come to the input output part. So this they have given, so already I have mentioned this is nothing but n input, this is not, second one 4 is nothing but m here, and the final one 2 is nothing but k here, right? nmk 542 they have given, right? nmk 542, and the forbidden ones are they have given here 1 2 2 3 4 2 and 4 1, right? So there are 4 this one 542, among the 542 we have 4 this one, what do we call this one accordingly with the question, these are the forbidden unordered pairs, right? So this is the integer k, this is fine, these are the unordered forbidden this one forbidden unordered pairs, nothing but 4 1 2 2 3 4 2 and 4 1, right? So these are the unordered forbidden pairs, basically 1 2 2 3 4 2 and 4 1, right? So these are the unordered forbidden pairs. So this is fine, man. Now we have nmk this one 542, and this one m we have already 4 1 2 2 3 4 2 and 4 1, nothing but the unordered this one forbidden pairs, basically. The final one is k, integer k we have 2, right? So this is fine. I believe the output that we need to get here is possible, meaning here here in this case at least one such tree exists, right? Accordingly with the criteria that they have given in the question, we have to check whether there exists a tree on n vertices such that none of the forbidden pairs are edges and vertex 1 has exactly 1 degree, right? So this condition matches, and in this case we have to return possible, right? For the second one, same goes with the second one as well. Here it is not possible, so it doesn't match the criteria, so in this case we have to go with the impossible, right? So we have to return impossible. This is fine, I believe. Now we have the understanding of the question, we have the understanding of the input output as well. Let's do one thing, let's quickly discuss the approach followed by the complexities, and then let's write the code. As usual, first let's discuss the approach. So we have considered the same first example that they have given in the question. So we have already discussed this one, so that it will be easier for us to consider for the same example for the approach as well, right? So n we have been given 5, m 4, and k we have been given 2. Forbidden, this one they have given 1 2, 2 3, 4 2, and 4 1. Right, one more thing that we need to observe here is we will be going with a BFS to solve this particular problem, right? So we'll be making use of the breadth first search mainly to solve this problem, right? So the first point here would be we'll be building ban of u that is equivalent to the set of nodes that we cannot connect to, right? So we cannot connect to, meaning forbidden edges, right? Forbidden edges. So this one 1 2 2 3 4 2 and 4 1. So we will be building ban. This one is just the variable name, you don't have to worry about it. We will be building ban of u that is equivalent to the set of nodes that we cannot connect to, nothing but forbidden edges. This one they have given in the input, right? So you can consider this one 1 2 2 3 4 2 and 4 1 for the example. So we will be going with a ban 1 of 2 4. We'll be going with a ban 1 of 2 4. This is fine. Now we have to count forbidden this one at just 1 forbid 1 that is equivalent to the number of forbidden pairs that involve vertex 1, right? So that involve vertex 1, we have to count forbidden 1 that is equivalent to the number of forbidden pairs that involve vertex 1. So we will be going with a can connect that is equivalent to the n minus 1 minus forbidden 1, nothing but 4 minus 2 that is equivalent to the 2. This is fine. The output that we got here is 2. So let's move on with the further things. Since can connect this variable if it is greater than or equivalent to the k, so meaning 2 is quite obviously 2 is equivalent to the 2, right? So 2 greater than or equal to 2 we will check. So we pass the quick feasibility check here. So we are going with the feasibility check, we pass it because 2 is equivalent to the 2 here by this one, right? So this is just the variable name, we are making use of the can connect. This has to be greater than or equal to k accordingly with the question, right? So k we have been given 2, and this one we have considered can connect as 2 as well. 2 greater than or equal to 2, yes, 2 is equivalent to 2, right? So we pass the quick feasibility check here. This is fine. Next we will be considering the nodes from 2 to n, and we will run BFS across the complement graph, right? One thing again, we will be considering the nodes from 2 to n, and we will run BFS across the complement graph. So we group the nodes into connected components of this complement graph. What we do, we group the nodes into the connected components of this complement graph, right? So there are 2 steps here. Again, we'll be considering the nodes from 2 to n, and we will run the BFS across the complement graph. So we group the nodes into connected components of this complement graph. Basically, right, the first point here would be we will start the BFS from node 2. We will start the BFS from node 2. From 2 we can go to 5, right? From 2 we can go to 5. From 5 we can reach 3 and 4, right? So you can just see here accordingly with the forbidden edges you can consider here, right? So we don't have to worry that much, right? We'll start the BFS from node 2, and from 2 we can go to 5, right? From 5 we can reach 3 and 4, right? So this BFS, what do we call BFS level by level, right? So this BFS reaches 2 5 3 4, right? So this is one of the components, 2 5 3 4, right? One component. The second point here is while BFSing, by making use of the BFS, we track whether the component has at least one vertex that can be connected to the one. So this one is the second criteria that they have given in the question, right? So while BFSing, what we do, we track whether the component has at least one vertex that can be connected to the edge 1, that can be connected to the edge 1, right? So the number of complement components is equivalent to the 1. So we need at most k components to attach. K here in our case it is 2. We need at most k components to attach vertex 1, meaning 2 components to attach vertex 1 for the example that we have considered, and here 1 is less than or equal to k, right? So 1 is less than k, meaning 1 is less than 2, quite obviously, right? So this is feasible here in this case. This is feasible. Therefore, the output that we will return here is possible, right? So this is the approach basically. Therefore, we have seen this one, BFS, right? So the 2 points, the 2 criteria that they have given in the question I have explained here. This is the second one. Previously I have explained the first one as well, right? So this one 2 5 3 4 what I have marked here. So this one is fine. So now the final point is number of complement components is 1, right? So that we got is 1. We need at most k components to attach to vertex 1, and here 1 is less than or equal to k, meaning 1 is less than or equal to 2 accordingly with the input that we have considered. So this is feasible. So output here, output we will return possible as output, right? So this is fine. So the final output here would be possible. The final output here would be possible. This is fine. The final output that we got here as possible. The output that we got here as possible, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So see here, output actually I haven't written. Basically output for this one is 1. Just give me a second here. So yeah, sorry, the output that we need to get here is possible, right? So 1 we got basically less than or equal to k, so we are returning possible. So the output that we got here is possible, which is equivalent to the output that they have mentioned for the example 1 within the question, right? So our approach works absolutely correct in this case, right? Our approach works absolutely correct in this case, right? So as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the complexity here? Time complexity basically. The time complexity and the space complexity both are big of n plus m. So why the time complexity here is big of n plus m? So here we will be processing every forbidden pair. So in our case it was having 4 forbidden pairs, right? So we will be processing every forbidden pair once, and each vertex is removed or visited once, exactly once, while BFS traverses the complement, right? So we are BFSing, right? So each vertex is removed or visited once while BFS traverses the complement. So overall work is proportional to n plus the total forbidden pair count as m, right? So this is fine, I believe. What will be the space complexity? The space complexity would be big of n plus m, because storing n hash sets and m forbidden links requires linear space. In this case, the overall space complexity would lead to big of n plus m. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n plus m and big of n plus m respectively, right? As we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come to the compiler here, one compiler. So we'll be making use of the fast input and the output. So let me import here this one. What do we call? Input output, right? Package basically. And also we'll be making use of the different utilities. So I'll just go with java.util.star. This is fine. So let's make use of the class here. So this one will be class. I'll just go with the main as usual. You can just give any class here, any class name basically that's relevant to the question, right? So inside the class, let's go with the main method. So within or with the main, I'll also give here throws exception as well. This is fine, man. Within the main method, let's do one thing. Let's go with the buffered reader and the print writer, right? So I'll just go with buffered reader, new buffered reader, new input, this one stream reader. So this is fine. System.n, right? So also we'll be going with a print writer. So this one will be print writer, put equals new print writer system.out. So this is fine. Now let's do one thing. Let's read the first line and split into the token. So I'll just give here string, this is fine, p equals buffered reader dot read line split. This is fine. Now we have to go with the, let's go with the number of vertices, number of forbidden pairs, also required degree of the vertex 1, right? So this will be nmk basically in simple terms. So this one will be integer dot %, dot we have to go with p, right? So this one will be p of 0. Let me do the same thing for this one, m and k as well. We just have to change this one index. So here this will be p of 1 and this will be p of 2, and also this will be m and this will be k. This is fine. Now this is the input output part, right? So we are just reading the number of vertices, number of forbidden pairs, as well as required degree of the vertex 1, right? So this is fine, k. And now let's go with the hash set. Why we will be going with the hash set here? Is hash set required here? So yeah, it is required. Actually I tried with the different things to solve, basically I'll not lie. So I was getting TLE, right? So that is the reason I made use of the hash set here, right? So this is nothing but the array of hash set. So I'll just go with ban of 1. So in the approach I have went with, right? So basically this is the variable. So just give me a second. Hash set, let me give it's of the type integer basically. This is fine. ban, let me assign this one to the new hash set of n plus 1. So let me go with the for loop here. Int I equals 1, I less than or equal to n. So this will be I plus plus. So again ban of I. So this one, let me go with a hash set. This is fine as well. So let's do one thing. We are just initializing each hash set for the vertices 1, right? So now let's do one thing. Let's count of the forbidden pairs that involve vertex 1, right? So initially let me initialize this one. We considered forbid 1, I believe. Let me consider the same thing here as well. Let me initialize this one 0. So this one, and the approach I showed for the forbid 1 variable, right? So this is the one, count of the forbidden pairs that involve vertex 1. So let's move on with the for loop here, in the iteration part in simple terms. So this one will be I equals 0, I less than m, I plus plus. So within the for loop, so let's read the forbidden pair first. So this will be string q equals buffered reader dot read line dot split. So this is fine, dot split. Again the same thing basically, right? So sorry, did I, yeah, this is fine. Now let's go with the, what do we have to go with? So let's go with the first vertex and the second vertex in the pair. So this one will be int a equals, sorry, so this is integer dot % of this one q of 0. This is fine. Let's do one thing. Let me copy this one. Yeah, so let me change the variable name to b here. This is fine. So this will be q of 1 instead of q of 0. This will be q of 1. Yep. Now we have went with the first vertex in the pair and also the second vertex in the pair. Now let's do one thing. Let's mark b and a as the b as forbidden for a and a as forbidden for b. Both are undirected, right? So now I can just write it in this way. Ban of a, this is fine, dot add of b. So pure graph based problems, right? So here ban of b. So this one, let me go with add of a, right? So this is fine, man. The final part here would be, if either of the endpoint is 1, then we have to increment the forbid 1. So here I can just write it in this way. If a equals 1 or b equals 1, then let's go with a forbid 1 plus plus. We are just incrementing this one, right? So let me come out of this one entirely. Now what we need to do, just give me a second here. as I've said, we'll be going with the BFS, that is different thing. So first we have to go with the number of vertices other than 1, right? So I'll just go with can connect. So I had considered can connect for the this one, right, within the approach. So I'll consider the same for the within the code as well. So I'll just go with n minus 1 minus 4 bit 1 we considered, yeah, 4 bit 1. This is fine. Now let's go with the if condition, simple if condition. This is for the quick impossibility check. When I say quick impossibility check, so I'll just go with here if. So let me go with can connect. If it is less than k, then what shall we do? So I'll just go with out dot println. So this is fine. So let me give here impossible. Impossible. This is fine. Let me give impossible. Also out dot flush. So this one, yeah, let me give out dot flush here. We have to flush the out, or you can just make use of the out dot close as well. So let me go with return. So we are just exiting. So we are just going with a quick impossibility check, right? So I have given return just for the sake of exiting. So this is fine. Let me come out of this one entirely, man. Now let's do one thing. Let's go with the ordered set of unvisited vertices among 2 to n, right? So I'll just consider tree set here. This is fine. S has to be capital here, or else we'll get the error. So this is fine. Integer. So I'll just go with the unvisited we are going with, right? So I'll just call this one unvis unvisited. So this one will be new tree set. So this is fine, man. Next, let's go with the iteration part. Initially all the nodes from 2 to n are unvisited itself. So I'll just go with the iteration part. So this one int I equals to I less than or equal to n. So let's increment the I here. So this is fine. Now let me give here unvisited. So let me add of this one I. This is fine. Yep, this is fine. Now let's do one thing. Let's count this one. Let's count the connected components in the complemented graph on nodes 2 to n. So this one, let me initialize component. So I'll just write CYMP here and count to 0, right? So this is fine. So while there are still nodes not assigned to the component, so if there are still nodes that are not assigned to the component, then we have to get and remove the smallest unvisited node to the to start the BFS. Basically, as I've said, we'll be going with the BFS, right? So that we will be doing. So if we have found a new component, then we have to increment the component count. That's what we need to do. Then let's make use of the BFS. So let's do that one first. While there are still nodes not assigned to the component, so let me write the simple while condition here. While loop here. This is fine. While not of unvisited. So this is fine. Dot is empty. This is also fine. Yep. Now let me give here int start equals unvisited. This one poll first. Poll first. So this is also fine. So the next step would be if we have found a new component, then we have to increment the component count, right? So this one, let me give component count plus plus. So let's go with the queue for the BFS. As I have said, we'll be making use of the BFS. Let's go with the queue for the BFS. Also, let's start enqueuing the node. Enqueuing this enqueue starting node, as well as let's go with the flag, meaning whether this component has a node connectable to the vertex 1. That we need to check, right? For that one, let's go with the flag. These three things, let's do this one quickly. First, let's go with the queue for the BFS. So this one will be queue integer queue. So we'll be making use of this one from the linked list. So this one queue linked list, right? So this is fine. And the next part is let's enqueue starting node. So this one will be, I'll be making use of the operation add here. Let me pass start. Simple. Final part here would be let's go with the flag whether we will be checking whether this component has a node connected to the vertex 1, the second criteria that they have given in the question. So let's make use of the flag here, boolean. I'll just go with the variable okay here. So this one not of ban of 1, so this one let me go with contains contents of, let me pass the start here. This is fine. Yep. Now let's do one thing, let's go with a while loop. So this one will be while not of q dot, well, q is not empty, right? So this is fine. Classic this one BFS. We are going with a queue. This is nothing but the standard BFS loop over the complement graph, right? So this is fine. Now let's go with the current node from the queue, meaning, so let me assign you to the queue dot poll here. This is fine. Yep. The next part would be let's go with the array list, man. Nothing but let's go with the temporary list for the newly discovered nodes to enqueue. That's what we need to do. We have to consider this one, right, at any cost. So I'll just go with array list of, so basically this consists of, this is of the type integer. This is fine. This consists of the integer itself. I'll just go with to add variable. So this one will be new array list. Yep, this is fine. The next step would be iterator. This one will be integer equals unvisited iterator. So this is fine. This has to be small one, small I. This is fine, man. So let's go with the iterator. That's fine. We're just iterating over the remaining unvisited nodes. And now let's write the one more while condition. So I hope this works, man. Let's see. So I'll just go with here dot has next here. This is fine. Then what we need to do, so we have to go with the candidate neighbor in the complement graph, in the sense, so let me assign the v to dot next here. This is fine. Next part would be if u and v are not forbidden, right? So suppose if u and v, so in our case there were 4 forbidden this one, right, edges. So if u and v are not forbidden, edge exists in the complement. So that's what we saw in the approach as well. So for that, let's write the simple if condition. So I'll just go with if here, if not of ban of u dot contains of v, this one, right? So v, then what we will do within the if condition, we will visit v in this BFS. So this one will be to add dot add of v. This is fine. The next part would be we have to remove v from the unvisited right away to avoid the revisiting. So this one will be t dot remove. This is fine, man. Yep, let me come out of this one entirely. Now let's do one thing. So let's go with the this one iteration part. So we need one more iteration. Let me write this one quickly. Int v of to add, right? So within this, what will be considering basically, if v is connectable to 1, then we have to mark this particular component okay, right? So I'll just go with if condition for this one, if not of ban of this one 1 dot contains here of this one v itself, right? So this one, let me go with true. This is fine. Now let's enqueue v for the BFS expansion. I'll just for the enqueuing, I'll be making use of the add operation, right? So this is fine. We have to pass v here. Let me come out of this one entirely, man. Now we are left with certain things. Basically we are left with certain things mainly related to the this one input output, right? So if that particular component has no node that can be attached to one, then this is impossible. For that one also we have to write the code, right? So for the impossible condition, so here I can just write it in this way, if not of okay, so this one will be out dot println. So this is fine. So this one will be impossible. So impossible. so this is fine. This one will be out dot flush. Out dot flush. This is also fine. Finally, let me give return here. Return just to exit, man. This is fine. Let me come out of this one entirely. Yep, let me come out of this one entirely. Now let's go with the simple if condition. If we need more than k connections to connect the components, then it is impossible, right? So let me write one more if condition for it. So I'll just go with if component count. So if it is greater than k, so then I'll just go with out dot println. So this is fine. So let me give here impossible. Yep, this is fine. Let me give here out dot flush. This is also fine. Finally, let me give a return here, right? So this is fine. Yep. Let me come out of this one entirely now. So we are left with only one thing. So here previously what we did, line number 71 to 74, whatever I have written. So this is nothing but if we need more than k connections, right? So to connect to the components, then it is said to be impossible, right? So then also we have to print impossible. So that's what we did. Otherwise, if these two conditions we have written for the impossible, right? So otherwise it will be possible, right? So otherwise meaning I can just write it here out dot println. But in the strings I'll just write here possible, right? So this is fine. Finally we have to flush the output. For that I'll just make use of out dot flush. This is fine. We are just flushing the output here. So we are done with the coding part, man. We are done with the coding part. So before checking the code with the different inputs, let me do one thing. Let me quickly copy paste the signature starter template. Just give me. So let me come here. Let me copy this one. So output that we need to get here as possible. Let's check the same here. Possible? No, not possible. Dot %. What the heck, man? So this one has to be within. So I don't know why I have given this one extra parenthesis I have given. So that is the reason it is screaming. Line number 39, 40, 39 and 40. Where it is 39, 39, 39. Yep. Let me remove this one. Let me remove this one as well. So let me run this one now. Yeah, we are getting the output possible, right? So I ignore the warning. It runs quite well in the this one Codeforces environment, so we don't have to care about that. So let me check this one. We have to get the output impossible. I hope we get impossible. Yeah, we are getting the correct output, right? So let me copy this one entirely. Let me come here to the question. Let me hit the submit. So we have successfully come to the submission part here. Let me paste the question solution here and let me hit the submit button. I hope this works for all the test cases, man. Let's see. Let's wait for some time. We are running on test 7, right? So let's wait for some time. Someone, this is slow sometimes, man. Let's wait for some time. How many test cases are there, man? 58. Yeah. So in the toast it is showing accepted. The verdict that we got here is accepted, right? So here we have went with a pure BFS to solve this particular problem, right? So we have went with a pure BFS including the queue basically. So BFS uses queue itself, right? So we have went with pure BFS to solve this particular problem. The two criteria mainly that I mentioned in the question, you can just pause the video or you can just rewind the video and you can just go there and you can just check where I have explained. The two criteria we have successfully this one, what do we call, satisfy those two criteria, we have just made use of the this one, what do we call, BFS. You can just check that. This is fine. Now this is it for the this is the solution basically for the question that they have asked, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.